Don't forget the mic, Natchez.
Yeah. Thanks.
Sharp.
Okay, we're gonna do this example, the one that I share on our WhatsApp group. Okay. This example that we're going to do. Sorry, okay. So question 5. We are given a figure shows two light rods AB and CD, each of length 0.6 meter, are hinged at A and C and carry concentrated masses of 1 kg each at B and D. The rods are coupled at their midpoints by spring of stiffness 500 Newton per meter, and then they want us to determine the dynamic equation of motion in a matrix form. So here they didn't specify that we should use which method, so you can use any method as long as you get the equation of motion. So you can use the Newton's second law method, or you can use the Lagrange method, the energy method. Okay, so now as you can see, we are given this figure. We have point A to B and point C to D. We have the masses. Okay, we have mass of 1 kg and 1 kg at B and D. Okay, so today we're gonna start with the Newton's second law method. It's more I think it's easier comparing to Lagrange, because Lagrange is long, but you will decide yourself which one do you want to use. But today we're gonna do the Newton's second law, and if we still have a time, I'm also gonna show you the Lagrange method. You'll see we're gonna get the same equation of motion. So we can use the Newton's second law in its rotational form, because you can see it's we have a mass. It's more like a pendulum. Okay, so here we can use the second law in its rotational form, same as sum of forces. Remember Newton's second law, it's F is equals to ma. Okay, F is equals to ma, but here we're gonna apply it as sum of moments. We're gonna use sum of moments equals to what? To moment of inertia multiplied by acceleration. Multiplied by acceleration. We know that we can also write acceleration like this in a rotational form. Okay, and then so we are given rods, two light rods, okay, which is massless and length 0.6 meter. Okay, so we also have a point masses, you can see at each end here, which is 1 kg. So we're gonna say our mass is equals to what? 1 kg. Okay, at point B and D, and we're also given what? A spring stiffness. K is equals to what? 500 Newton. This one, Newton per meter. This one. So it connects the midpoints of what? Of the rods. So it connects these midpoints of these rods. Okay, so it's in between. And then we're gonna also have what? A midpoint distance from hinge to what? From hinge. So we're gonna have L over 2, which means it's gonna be what? L over 2, which means it's gonna be what? 0.6 divided by 2, which is what? 0.3 meter. This one from here to here, we call this a midpoint. So we have a midpoint distance from hinged. So it's what? It's 0.3. This 0.3 is going to help us to determine the length of stiffness. When we're calculating stiffness, the forces, we're going to use the L over 2. So we also have what? We're going to have a small rotation angle about the hinge. So we're going to have a theta 1. So we're gonna have a theta 1. You can see we have the light rods here. So let's say it moves. So we're gonna have a theta 1 here. Also gonna have a theta 2 here. Okay. And then here is gonna be L over 2. Then here's gonna be L over 2. Here it's A. Here it's what? It's C. Okay, so we're gonna have a small rotation angles about the hinge. So we're gonna have a theta 1 and theta 2. Okay, so let's just open another page. So here, remember we say we're gonna do the moments, the Newton's second law. So then we're gonna use the sum of moment is equals to the moment of inertia. So moment, rotational newtons for the left rod. We're gonna start with the left rod, the A1. Okay, so we're gonna start with the moment. Moment forward for left rod. Okay, we're gonna start with the moment for left rod. So it's gonna be about what? Hinge A. It's gonna be about what? Hinge A. So rotational form of Newton's second law about hinge is gonna be the sum of moment at A equals to what? The initial moment of inertia at A multiplied by what? By acceleration. Multiplied by acceleration. Like this. Okay. Like this. And remember the moment of inertia is going to be J equals to what? To ML squared. Okay. So here we need all moments restoring or tending to return to equilibrium acting on the left rod about A. So we're going to start with what? With the gravity. Okay, we're going to start with the gravity. So for small rotation theta 1, the tangential components of weight produces a restoring moment. So we're going to have, here we're going to start with the gravity one. So the force of gravity F is equals to a negative mg theta 1. So remember here is for small rotation theta 1. So the tangential components of weight produces a restoring moment. So it's going to be F is equals to a negative mg theta 1. So this negative sign, it indicates it opposes what? A positive theta 1. This negative sign, it indicates it opposes positive theta 1. Okay, and then the moment about hinge A for gravity. Remember, moment it's force multiplied by what? By length. So the moment of gravity is gonna be what? Force multiplied by length, and our force is what? Is negative mg theta 1. Okay, so we're going to multiply this negative mg l theta 1 with what? With length, and then we get what? The moment. We get what? The moment. So moving forward, we're gonna have the moment. The moment at A for gravity is gonna be a negative mg theta 1 multiplied by what? By length. Remember, moment it's force multiplied by length. Our force is what? Is negative mg theta 1 for what? For small rotation theta 1. And therefore we can just write it like this, negative mgl theta 1. Okay, now we are done with what? With the gravity. So we have the moment at A for gravity, and now we can focus on the spring. Remember, we are doing the first rod on the left, the A to B. Okay, and then now on the spring we're gonna do the spring one. Okay, so the spring connects the two midpoints for small rotations. So the horizontal displacement of the left midpoint is gonna be L over 2 theta 1. L over 2 theta 1. Remember, the spring is is in the middle, is the midpoint. Okay, so we're gonna have L over 2 theta 1. Let's call this one our x1. Okay, and then this one is gonna be to the right, positive, and the right midpoint, the right midpoint is gonna be L over 2 theta 2 equals to what? Let's say this one's gonna be our x2. Okay, so the spring extension is gonna be what? X1 minus x2. Our x1 is L over 2 theta 1 minus L over 2 theta 2. Okay, this is the spring extension. Okay, here we are doing spring. And then here I was just explaining that the spring connects the two midpoints for the small rotations, the horizontal. So the displacement of the left midpoint, this is the displacement of the left midpoint, and then this is the displacement of the what? Of the right midpoint. So the extension of the spring is gonna be this displacement x1 minus x2. So we're gonna have what? L over 2 theta 1 minus L over 2 theta 2. Okay, and then we all know that the force for spring is what? Is negative K multiplied by what? By extension. It's gonna be the force of spring, it's negative K multiplied by what? By extension. Remember, our extension is L over 2 theta 1 minus L over 2 theta 2. So we're going to substitute our extension here. We're going to have a negative K multiplied by L over 2 theta 1 minus L over 2 theta 2. And then here we can just take out the common factor as our common factor of L over 2. And now we're going to be left with what? With a negative K L over 2 into theta 1 minus theta 2. Okay, so this is spring force. Okay, but remember, we want the moment. So the horizontal spring forces is going to produce a moment about A because it acts at what? At a distance L over 2 from the hinge. So the moment on the left rod for the spring is going to be this moment of spring at A. Okay, let me just write it like this. Moment at A for spring is going to be what? The length multiplied by force. Remember, moment is length multiplied by what? By force. Distance multiplied by what? By force. So it's going to be L over 2 multiplied by what? By force. And remember, our force is what? It's negative KL over 2 into theta 1 minus theta 2. So we're going to have L over 2 multiplied by a negative K L over 2 theta 1 minus theta 2. Okay, like this. And then after here, we can just multiply these two. We're going to have a negative K L multiplied by L, we're going to have L squared. 2 multiplied by 2, we're going to have 4 here. And then we're going to have something like this. So we have the moment of spring. We also have the moment of gravity on what? On the left rod. On the left rod, the hinge at A. Okay, so we have the moment of spring. We also have the moment of gravity. So here we're going to add the moment of spring and the moment of gravity. Remember, here we're dealing with what? With the Newton's second law. And the Newton's second law here is going to be the sum of all moment at A is going to be equals to what? To the moment of inertia multiplied by acceleration. So here we're going to add all the what? The moments. So we're going to total moments about A. Okay, about hinge A. Okay, so it's going to be sum of moment is equals to moment of inertia at A multiplied by what? By acceleration. acceleration 1, because we are dealing with the left rod. Okay, so here at the moment we have the moment of gravity, we also have the moment of what do you call spring. So the moment of gravity, it was negative mgl theta 1, and the moment of spring, okay, let me just write here that here at moment we're gonna have the moment of gravity at A plus the moment of spring at A, or equals to, remember the J is equals to ml squared, so it's gonna be ml squared theta dot dot 1, like this. And then the moment of gravity at A, it was negative mgl theta 1, and then the moment of spring at A, it was what, a negative k l squared over 4 into theta 1 minus theta 2, or equals to ml squared theta 1 dot dot. Okay, it's gonna be l squared theta dot dot 1, okay, like this. And then from here we can take this moment to the right, so we're gonna have ml squared theta 1 dot dot plus mgl theta 1. Here we can multiply this kl squared over 4 multiplied by theta 1, we're gonna get a negative, and then if we take it to the other side, it's gonna be what, a positive kl squared over 4 theta 1, and the negative kl squared over 4 multiplied by negative theta is going to be a positive, and then when it goes to the other side, it's going to be a negative, so it's going to be a negative l squared over 4 theta 2, all equals to 0. They are all equals to 0. Okay, so this is our first equation of motion. Okay, this is our first equation of motion. We have ml squared theta dot dot 1 plus mgl theta 1 plus kl squared over 4 theta 1 minus k l squared over 4 theta 2. So here you can see we have theta 1 and theta 1. We can take out common factor of theta 1. So we're going to have so we're going to have m l squared theta dot dot 1, so here's theta dot dot 1 plus theta 1 into mgl plus k l squared over 4, like this. Here we just take out the common factor of theta 1 minus kl squared over 4 theta 2. Okay, this is theta 2, or equals to 0. So this is going to be our first equation of motion using what, Newton's second law. And then when and then let's go and do the right rod. We are done with the left rod. Okay, now we're gonna do the right rod, the one that it's hinged at C. Moment for right rod about hinge C. Okay, before we do the right rod, do you have any question here on the left rod? Sorry, do you have any question, guys? Okay, let's move forward and do the moment for right, moment for right rod. Okay, for right rod about what, about hinge C. It's taking time. Okay, I just wanted to show you that we're gonna do this moment at C here. Okay, at C. We are done with the left rod. Now we're doing the right rod. Okay, so here on the right rod, what's going on? Okay, sorry. So we're gonna do the moment for the right rod about hinge C. Okay. And you can see that the left and the right is the same. They have 1 kg masses. They have same length. The spring is in between. So by the exact symmetry, the equation for the right rod is the same as what? Is the same as left rod. So with indiced what? Strapped. So wherever there is theta 1 on our first equation, we're going to replace it with theta 2. So we had m L squared theta 1 dot dot in our first equation, okay, plus mgl plus k L squared over 4 multiplied by theta 1 minus k L squared over 4 multiplied by theta 2. So this was our first equation of motion, and now we are saying what? By the exact symmetry, the equation for the right rod is the same as what? It's the same as the equation of left rod. So which means wherever there's theta 1, we're going to replace it with what? With theta 2. So this is going to be our first equation, and then our second equation is going to be ml squared theta 2 dot dot, okay, plus mgl plus k L squared over 4 theta 2. This one is going to be our second equation, okay, minus kl squared over 4 theta 1 or equals to 0. So this one is our second equation. Okay, do you have any question, guys? Okay, seems like you don't have any question. And then the second question, we're not done. We have equation 1 and equation 2, and they want us to write our equation in a matrix form. So we have equation 1 and equation 2. So in equation 1 we have a theta dot dot 1, a theta 1 and a theta 2. Even on equation 2 we have a theta dot dot 2 and theta 2 and theta 1. So now we can write our equation of motion in what? In a matrix form. So we're going to have something like this. The first one is going to be for mass, theta dot dot 1, then theta dot dot 2. Can't write dot dot. What's wrong? Like this, plus this one is gonna be for what? For stiffness. The first one is gonna be for mass, and then the second one is gonna be what? For stiffness. And then our mass here you can see we have ml squared theta dot dot 1. So we're gonna take the coefficient of theta dot dot 1, and here we're also gonna take the coefficient of theta 1. Here we're gonna take the coefficient of theta 2. So the coefficient of theta dot dot 1 is ml squared, and then for theta 1 is mgl plus kl squared over 4, and then for theta 2 it's negative kl squared over 4, same as this equation 2. Okay, and then now we're going to have the ml squared here for theta dot 1. So in our first equation, we only have a theta dot 1. We don't have a theta dot 2. Theta dot 2, that's why we're gonna write what? 0 here. And then what did I write? Well, here it's ml squared. And then on our second equation, we don't have a theta dot 1. We only have what? Theta dot 2. So it's gonna be what? 0 here, and then here we're gonna have ml squared. Okay, and then now this one is for what? Is for mass. And now let's come to what? To stiffness. Let's come to stiffness. All this are equals to what? To 0, because we don't have forces. If we had forces, we were gonna be equating them to what? A force. And then now we come to this to the stiffness. We're gonna start here on the first equation. We're gonna check theta 1. Our theta 1 is mgl plus kl squared over 4, and our theta 2 is negative kl squared over 4. Okay, so here we're going to have mgl plus kl squared over 4, and here we're going to have a negative kl squared over 4. Okay, same here on the second equation. Oh, sorry, here's 2, not 1. On our second equation, we're going to have a negative kl squared over 4. Here we're going to have mg l plus kl squared over 4. Okay, kl squared over 4. So this is how our matrix is gonna look like, and then we can substitute the values. Remember, the mass, it's 1, the L, it's 0.6 meter. What else? K is 500, right? So we can substitute here, and then we're gonna be having this. So it's gonna be 1 multiplied by what? By length, 0.6 meter squared. So it's gonna be what? It's gonna be 0.36. So it's gonna be 0.36, and then here we have 0, then here 0, and then here 0.36, because it's the same, because we only have one mass, which is 1 kg. Plus here we're gonna write the stiffness. So it's gonna be 1 multiplied by 9.81. So this is acceleration, g, gravity. So it's equals to what? To 9.81. So it's gonna be 1 multiplied by 9.81 multiplied by length. Our length is what? Is 0.6 meter. So it's gonna be 1 multiplied by 9.81 multiplied by 0.6 plus 500 multiplied by 0.6 squared divided by 4, which will get a 50.8. So here we're gonna have 50.8. Okay, and then here it's gonna be a negative 500 here, a negative 500 multiplied by 0.6 squared divided by 4, and then we're gonna get what? A negative 45. A negative 45. So here we're gonna have a negative 45. Okay, same as here, it's gonna be a negative 45. Okay, and then even here it's gonna be 1 multiplied by 9.81 multiplied by 0.6 plus 500 multiplied by 0.6 squared over 4, and then it's gonna be what? A 50.8. And then this is how we write our matrix. So here on the side, it's going to be a theta dot 1, theta dot 2, and then this side is going to be theta 1, theta 2, or equals to what? Or equals to 0. Okay, so this is how we do, this is how we do, this is how we determine the equation of motion using Newton's second law. Okay, using Newton's second law. After here, they ask us to determine normalized stiffness. Let me just go back a bit. So now we are done with the first equation, with the first question, where they say we have to determine the dynamic equation of motion in a matrix form. Okay, we substituted and then we get our answer in a matrix form, which was 0.36, 0.36 plus the 50.8 minus 45 and 50. And then the second equation, the second question, they say determine the normalized stiffness. So to determine the normalized stiffness, we have the formula. To determine the normalized stiffness. So the formula for normalized stiffness, it's K. Let me just erase this part here. So to determine the normalized stiffness, we have this formula, a negative 1/2 multiplied by K multiplied by mass over 2 to the power of negative 1/2. So this mass is the one that we write it in a matrix form, and then this K is the one that we write it in a matrix form. Okay, so we're just gonna write our masses in a matrix form and the K in a matrix form, and then we calculate it from them. Okay, so this is what I'm saying, I'm talking about. Okay, so this is our mass, this is our stiffness. So in our equation, remember we have K equals to m to the power of negative half K multiplied by m to the power of negative half. So wherever there's m, we're gonna use this matrix, the 0.36, 0, 0, 0.36, and wherever there's K, we're gonna substitute with this. Okay, so this is what I'm saying. Of 5.2, they want us to determine the normalized stiffness. So the formula for normalized stiffness, it's m to the power of negative 1/2 K m to the power of negative 1/2. Or you can just multiply these two, because they say if the bases are the same, we add what? The exponent. So you can also write it as m to the power of negative 1 multiplied by K. Okay, still the same formula. Okay, and then here we're gonna substitute our matrix. We're gonna have it's 0.36, it's 0, 0, and 0.36, all to the power of negative 1. Okay, multiply by the stiffness. Our stiffness, we have a 50.8 and 45, a negative 45. And then here we have a negative 45, and then here we have a 50.8, like this. Okay, so after here we're going to do this. We're going to have it 0.36 to the power of negative 1, 0 to the power of negative 1, 0 to the power of negative 1, and then 0.36 to the power of negative 1. Okay, like this. And then we have a 50.8, a negative 45, a negative 45 here, and then a 50.8. Okay, this is 50, a 50.8. Okay, and then now you're gonna calculate the 0.36 to the power of negative 1. You're gonna get the answer, 36 to the power of negative 1. You're gonna get the answer, which is 2.78. Okay, and then after getting the answer, you're gonna write it here. So we're going to have a 2.78, and then here 0, 0, and then here 2.78, and then you're just gonna copy this, the 50.8, negative 45, and a negative 45 there. Okay, a negative 45 and 50.8, and then now from here we want it to be in one matrix form, so we want only one box, so we're gonna multiply. So to multiply, we're gonna say this 2.78 multiplied by 50.8, so 2.78 multiplied by 50.8, okay, plus, let me change the color, plus 0 multiplied by negative 45. So it's going to be 2.78 multiplied by 50.8 plus 0 multiplied by negative 45. And then we're going to get what? We're going to get the answer. So we're going to get what? 2.78 multiplied by 50.8. It's going to be 141. 141.2. Okay, so now we're done with the first corner here, and then now let's do this corner. So to do this corner, it's gonna be this 2.78 multiplied by negative 45, and then I was supposed to change the color. So we're gonna say this 2.78 multiplied by negative 45, okay, multiplied by negative 45 plus 0 multiplied by 50.8. So it's gonna be 2.78 multiplied by a negative 45, and then we're gonna get what? A negative 125. So here we're gonna have a negative 125. Okay, same as this one. This one's gonna be 0 multiplied by what? Multiplied by 50.8, and then plus 2.75 multiplied by negative 45. So and then here we're gonna get what? A negative 125, and then here we're gonna get a 141.2. okay, 0.3, because we round it off. 0.3, 141.3. okay, so this is how we determine normalized stiffness. Do you have any question, guys, here on normalized stiffness? Hello? Okay, you can also use this one here on 0.36. You can say 0.36 to the power of negative 1 over 2, and then do the same thing, and then, but it's long, that one, it's long. I think this one, it's easier when we have m to the power of negative 1 multiplied by k. Okay, but you can use any one in these two. Okay, guys, do you have any question under normalized stiffness? If you don't have, we're gonna move forward and do the next question. Guys, are you following? You can just raise your hands and then, oh, okay, thanks, Kuliso. Sharp. And then number 3, this, they want us to determine what? Number 3, they want us to determine the natural frequency of the system in radius per second. They want us to determine what? The natural frequency in what? In radius per second. So now let's determine the natural frequency in radius per second. And then the second question, it wants us to determine the eigenvalues and eigenvectors. Okay. Okay, number 3, (5.3), they want us to determine the natural frequency, and it's natural frequency, right? Yeah, natural frequency. So to determine the natural frequency, we're gonna use the determinants. So we're gonna use this formula, determinant of a normalized stiffness minus eigenvalue multiplied by I, or equals to 0. So all the time this I is gonna be equals to what? To 1001. All the time the I is going to be equals to 1001, like this. Okay, so what we're going to do here, we're going to substitute what we have. We have the normalized stiffness. Remember, the normalized stiffness, we get what? 141.3 and negative 125 and 141.3. okay, and then we're going to substitute that. After that, we're going to determine what? The natural frequency. Sharp. So now let's substitute. We have the determinant of this. Remember the normalized stiffness, our normalized stiffness, it was 141.3 0.3, negative 125, negative 125, 141.3. Okay, let's close bracket, minus lambda into what? Into 1001, or equals to what? Or equals to 0. So or equals to 0, and then from here we're gonna multiply this lambda with 1001. Okay, we're gonna multiply it, so we're going to have the determinant of this, the 141.3, the negative 125, negative 125, 141.3. okay, minus into, we're gonna have a lambda here, 0, lambda, and then 0. Sheza, I'm lying. Mistake here. It's gonna be it's gonna be negative into lambda, 0, 0, lambda. Okay, or equals to 0. Okay, so from here we're gonna say 141.3 minus lambda. 141.3 minus lambda. Okay, so we're gonna have 141.3 minus lambda, and then minus 125 minus 0, so we're gonna have a minus 125 here, minus 125 minus 0, so we're gonna have a minus 125, or 141.3 minus lambda, so here we're gonna have 141.3 minus lambda, or equals to 0. Or equals to 0. Remember, it's a determinant. We have a determinant on the side, so we're going to have something like this. And then remember, it's determinant, so if it's determinant, this part is gonna multiply with this, so we're gonna have a 141.3 minus lambda multiplied by 141.3 minus lambda, minus, we're gonna multiply this too, so it's gonna be minus negative 125 multiplied by a negative 125, or equals to what? Or equals to 0. And then now we can solve for what? We can solve for lambda. Okay, so it's gonna be 141.3 multiplied by 141.3, so, and then we simplify. Okay, after simplifying, we're gonna have something like this. We're gonna have lambda squared minus 2 point minus 282.7 lambda plus 4,354.8. okay, 0.8, or equals to 0. Oopsie, what did I do now? Or equals to 0. Okay, and then we're gonna solve for lambda 1 and lambda 2. You can use the quadratic equation. So lambda 1, we're gonna get 16.35. okay, and then lambda 2, we're gonna get 266.35. guys, we call this eigenvalue. So we have our eigenvalues. So lambda 1 and lambda 2, we call them eigenvalues. Okay, and then to get natural frequency equals to, natural frequency is equals to this. And then natural frequency is gonna be what? Square root of lambda. So to get a natural frequency, we're gonna have a natural frequency 1, which is gonna be a square root of lambda 1, and then a natural frequency 2 is gonna be a square root of lambda 2. Okay, so it's gonna be natural frequency 1 square root of 16.35, square root of 16.35, which is 4.044 radius per second. Okay, and then frequency 2 is gonna be a square root of what? Of lambda 2, square root of lambda 2, which is square root of what? 266.35, which we're gonna get what? A 316.32 radius per second. Okay, this is how we get, we get natural frequency. We start by writing the formula, the determinants of what? Determinants of where is it? This, oh no. Okay, it was determinant into a normalized stiffness minus lambda multiplied by I, like this, or equals to 0, and then you substitute your values. After substituting, you're gonna do the determinants and then get the eigenvalues, the lambda 1 and lambda 2, which we call them what? Eigenvalues. And then this W, we call them natural frequency. When they say determine natural frequency, you use the determinant formula, which is determinant into normalized stiffness minus lambda I. Okay, this is a natural frequency. Guys, do you have any question here under natural frequency? Okay, let's move and then do number. This was number what? This was number 3. Number 4. Number 4, they want us to determine what? Eigenvector and eigenvalues. But we've already done eigenvalues. So our eigenvalues, it's 16.35 and 266.35. So now here we can determine what? The eigenvector. Okay? We can determine eigenvector. So here under eigenvector, they want 5.4, they want us to determine eigenvalue and eigenvector. So our eigenvalue was 16.35. We already determined the eigenvalue, and then this one was 266 point what? 0.35.3. It was 266.35. Okay, and then this is our eigenvalue, and then to determine eigenvector, we have the formula for eigenvector. So for eigenvector, we're going to have vector 1 and vector 2, since we have 2 eigenvalues. Okay, so we're going to have v1 and v2. Okay, so the formula for v1 and v2, it's what? We have the formula for v1 and v2. Where's that formula? Okay, before writing this formula, to determine the eigenvector, we're going to use this formula for eigenvector. We're going to have a normalized stiffness minus lambda 1, okay, multiplied by I, or multiplied by v1. So we are going to look for v1. V1 is vector. It's vector. Okay, so which means v1 is we're gonna work v1 with what? With lambda 1, which is 16.35. okay, so what we're going to do, we're going to substitute the normalized stiffness and I. Remember I said it's 1001, and then we have the value of lambda 1. So our normalized stiffness was 141.3 and negative 125, 141.3, all minus lambda 1. Our lambda 1, it was what? 16.35 multiplied by 11001, like this, v1. Okay, or equals to what? Equals to 0. So here on v1, we can write our v1. Remember here we just write v1 and we want a matrix. So v1, we can write our v1 as 1 v21 in a vector form. So we're going to look for v21, and then after getting V21, the formula for V1 is going to be 1 over square root of 1 squared plus V21 squared, like this, and then with the vector 1 V21. Okay, so what I'm saying here at V1, we're gonna write this V1 as a vector, so it's gonna be 1 V21, and then we're gonna look for V21. You can use any number here. When we say V21, you can use V11, V0, V22. Okay, so here we just write a V1 in a vector form. So I'm gonna rewrite this matrix into a V1, V21, and then after getting V21, we're gonna substitute into this formula to get what? To get vector 1. To get vector 1. Okay, let me just rewrite it. We have So remember, we are using this formula, lambda 1 I V1 is equals to 0, and then I say V1, we're going to write it in a vector form, V21, and then I said this V21, we can write V22 or V11, it's up to you. So our formula is going to be K, normalized stiffness, minus lambda 1 I, like this, 1 V21, okay, or equals to 0. Okay, the reason why we're writing this in a vector form is because our matrix form, our normalized stiffness is in a matrix form. So we're gonna have a 141.3 minus 125 minus 125, 141.1, 141.3, okay, minus a 16.35 into 1001, okay, all multiplied by 1 V21, okay, or equals to what? Equals to 0, or equals to 0. And now here we can multiply this 16.35 multiplied by 1 multiplied by 0, and then we're gonna get what? So let me just rewrite this, 141.3 minus 125 minus 125, then we have 141.3. okay, so it's gonna be minus into 16.35 multiplied by 1, we're gonna have a 16.35, and then here we're gonna have 0 0, and then here 16.35, okay, all multiplied by 1 V21, okay, like this, equals to 0. That all equals to 0. After here, what we're going to do, we're going to say 141.3 minus 16.3. 141 minus 16.35. 141.3 minus 16.35. It's gonna give us what? 124.95, which we can run it to 125. So it's gonna be this minus this, which is gonna be what? A 125, okay, and then minus 125 minus 0, we're gonna have a negative 125, and then negative 125 minus 0, a negative 125, this minus this, okay, and then 141.3 minus 16.35, we're gonna get 124.95, which we can run it to what? To 125, all multiplied by the vector 1 V21, or equals to 0, okay, or equals to 0. And then from here we can now solve for V21. Remember, if it's on this side, we can also write it here, V21, which means this 125 is going to multiply with 1, and then this negative 125 is going to multiply with V21. So we're going to have two equations, but you can use any, you're still going to get the same answer, okay. So we're going to have 125 multiplied by 1 minus 125 multiplied by V21 equals to 0. Or we can have a negative 125 plus 125 V21 is equals to 0. So this is what I'm saying. From our matrix, we have a 125, a negative 125, a negative 125, we have 125, and 1 V21. or equals to 0. Our sign here is still the same as this. So we're gonna have two equations. We're gonna have a 125 multiplied by 1, which is 125, minus 125 v21 equals to 0. Or we can have a negative 125 minus plus 125 v21 is equals to 0. So this is going to be our first equation. This is going to be our second equation. We can use any equation here to get v21. Okay, so our v21, if we use the first equation, v21 is going to be what? We're going to take this 125 to the other side. It's going to be a negative, and then we're going to divide both sides by what? By negative 125. And then v21 is going to be what? It's going to be 1. And remember, we are looking for vector 1. Okay, so v1, it's equals to 1 over square root of 1 squared plus v21 squared. Okay, multiplied by what? By our vector 21. Okay, like this. And then we can substitute the vector, the vector 21. So it's going to be, v21. So it's going to be 1 over square root of 1 squared plus 1 squared into 1 1, like this. And then we're going to get the answer. 1 over square root of 1 squared, or you can say 1 over square root of 1 squared plus 1 squared. We're going to get what? It's 0.70. So we're going to have a 0.70 into 1 and 1. And then we can just multiply 0.70 with 1 and with 1. So therefore our v1 is going to be 0.707. And then we're still going to do the same thing on v2. Remember, we started by using lambda 1. Our lambda 1, it was 16.35. And then now we want v2. To get v2, we're going to use what? We're going to use lambda 2. Lambda 2, it was 266.35. And then we're going to use the same equation where we have the normalized stiffness minus lambda 2 multiplied by I. Here is going to be v2. Okay, it's equals to 0. But remember, we want our v2 in a vector form. We can write our v2 like this: v1 1. Okay, here we just we're gonna start with v on top and then 1 on the bottom. Remember, on the first one we start by 1, and then on the bottom we write v. Okay, so our v2 is going to be v1 1. Okay, remember here at v you can use any values. You can use v22, v31, any number. Okay, so now we're looking for v2. We're still going to follow all the steps that we did on v1. Okay, so we're going to substitute the normalized stiffness. We're going to substitute the eigenvalue 2, and then I said it's 1001, and then we're going to substitute with this v11, and then after getting v11 we're going to solve for v2. So our v2 is going to be 1 over square root of 1 squared plus v11 squared or v111. Okay, like this. So this is the formula for v2, and then we're going to substitute, and therefore at the end our v2, I'm not going to solve, you're going to substitute this whole thing and then solve for v11. After getting v11, you're going to substitute it here, and then at the end our v2 is going to be, our v2 at the end is going to be a negative 0.707 and 0.707. Okay, remember our v1 was a 0.707. So this is how we determine the eigenvector. Okay, so we're gonna get v1 and v2. Okay, all the time we use that formula. We use this formula to determine what? To determine the vector, and then we're gonna write v2 in a vector form. Okay, that's it. And then the last part, 5.4, they want us to determine the modal matrix and the spectral matrix. Okay, they want us to determine the modal matrix and spectral matrix. Okay, so to determine the modal matrix, so we have the formula for modal matrix. The modal matrix is P equals to V1 V2. Okay, remember we determined the vector 1 and vector 2. So our vector 1 was 0.707 like this, and our vector 2 was negative 0.707 and 0.707. So we call this what? A modal matrix. This is a modal matrix. When they say determine the modal, you just write your equation and then substitute V1 and V2, and then you're gonna get your answer. Okay, and then when they say spectral matrix, this is the formula for spectral matrix, which is P to the power of T K multiplied by P. Okay, so here you just substitute this is the normalized stiffness, so it's P to the power of T multiplied by normalized stiffness multiplied by P. P is modal, so this one is just an inverse. You just swap this PT, you just swap. Oh, Cheza, you just swap here at P to the power of T. So this negative is gonna come here, so we're gonna have 0.707 and minus 0.707 and then 0.70. So you just swap this two, take this negative to here, and then it's gonna be like this. The P to the power of T is the inverse of what? Of the modal matrix. So you just swap this one, and then you're gonna take this matrix for P to the power of T, and then you will know the matrix of normalized stiffness. Will also know the matrix of P. So you just substitute, and then the spectral is gonna be P to the power of T K P, like this. So we're going to have a 0.707 minus 0.707, 0.707. So this is for P to the power of T, and then for K, remember it's gonna be multiplying. Okay, and then for K it was 141.3, negative 125, and negative 125, and 141.3. Okay, and then our P it was 0.707, negative 0.70. A negative 0.707. Here it's 7. Okay, and then here we have 0.707, and then also here we have the 0.707. Okay, like this. But at the end of this, when we multiply, when we do the determinants, blah blah blah, it's gonna give us this. We're gonna end up having lambda 1, 0, 0, and lambda 2 at the end. So in summary, we can say this modal matrix, this spectral matrix is the same as what? As eigenvalues. So at the end, you can just say the spectral matrix is equals to 16.35, 0, 0, and 266.35 at the end. But you have to write this. Okay, after writing this, you can write, okay, the matrix, the spectral matrix is equals to lambda 1, 0, 0, lambda 2, and then you substitute. You don't really have to multiply this 0.7 with 143, blah blah blah. No, you can just write it like this and then write that, or okay, the spectral matrix is lambda 1 0 0 lambda 2, and then you substitute the value of lambda because you have already calculated. So guys, this is how we solve that quotients. So you can use the Newton's second law method or Lagrange. So here we were using the Newton's second law method, where we were using the sum of moment at point A, at hinge A, and sum of moment at hinge C. Okay, and then we get what? We get the equation of motion. If we were using Lagrange method, remember Lagrange method, we want energies. We can call it a method, energy method, where we have the potential energy and kinetic energy. Okay, so let me just show you if you were supposed to use Lagrange method. Okay, so if still on that question, remember we were given the light rod with mass like this, and then we have a spring in between, and then here we have point A, here we have point C, point C, and then here's C and D. This is a mass, these are masses, which is 1 kg, and then we have the spring. Okay, it's hinged like this. And if we were using Lagrange method, we have it's L is equals to T minus U, the kinetic minus potential. First, we're gonna look for potential for kinetic T. Okay, equals to, for T, it's gonna be the first mass at C and the second mass at D. So it's gonna be half. Remember, it's rotating, so it's gonna be like this. We're gonna have a theta 1 and then a theta 2 here, with the mass in between, with the spring in between. Here we have a spring, so it's gonna be a theta 1 minus theta 2 for the spring, K. And then here, from here to here, is gonna be L over 2. It's gonna be L over 2 because the spring is what is in between. The spring is in between. So here we're gonna have half, because it's rotating, it's the moment of inertia multiplied by what, the acceleration, plus half. So this is 1 for what, for A. This the hinge at A, we're gonna say it's 1, and then at C we're gonna say it's 2. So we're gonna have the moment of inertia at 2, which is C theta 2 dot dot. Okay, and then we know that J is equals to what, ml squared. Remember, this one, it's a light rod. Okay, so we're gonna have a half ml squared theta dot dot 1. Okay, plus half ml squared theta dot dot 2. Okay, like this. So this is our kinetic energy. And then when we want potential, for potential, we're gonna have for 1, and we're also gonna have potential for 2 at A, and potential energy at C. We're also gonna have a potential energy for what, for spring. So now let's start at A. We're gonna have m1 gl into 1 minus cos of theta. Okay, plus for C, it's gonna be m2, but it's the same masses, and then here it's gonna be theta 1, m2 gl into 1 minus cos of theta 2. Okay, plus, remember, we have a stiffness, and then this stiffness is in between two light rod. It's in between two light rod, and then our length here, it's what, it's L over 2. So we're going to have a half K for stiffness into L over 2 theta 1 minus, is it theta 1 or theta 2? Yeah, theta 1 minus L over 2 theta 2. Okay, all squared like this. So this is going to be our potential energy. It's gonna be our potential energy.
To get kinetic energy, don't we have squared on the theta dot dot?
Oh yes, we do. Thank you. We do. Thanks. Yes. Thank you for this. Okay, so here this is our potential for the A, and then this one is for C, and then this one is for stiffness. Okay. And then moving forward, remember we are using the Lagrange method. So we have that formula for Lagrange where we have the d over dt into partial derivative of kinetic over partial derivative of qi. So this qi is generalized coordinates. Remember we have a theta 1 and theta 2. So qi, we're going to let qi is equals to theta 1 and theta 2 so that we can get the two equation of motion, because we have what? Two generalized coordinates. And then minus partial derivative of t over this plus this, or equals to 0 because we don't have force. If we have force, okay, let me just write here qi is equals to qi, and now we're gonna let qi equals to theta 1. So we're gonna start by focusing on what? On theta 1. So it's gonna be d over dt into partial derivative of t over partial derivative of theta dot 1, like this. We are focusing on what? On theta 1. Or equals to 0 because on the first rod we don't have any forces. Okay, and from here we're gonna go to what? To our kinetic energy and check wherever this theta 1. We're gonna derivate wherever this theta 1. So we have a theta 1 here. The derivative of half ml squared theta dot dot squared 1 is gonna be what? So it's gonna take this 2 and multiply with half. So we're gonna left with what? With ml squared theta dot dot 1. Okay, so here we're going to have the d over dt into ml squared theta 1 dot dot. Okay, like this, minus, and then we go back to our t. On t, do we have a theta 1? No, we only have a theta dot dot. We don't have a theta 1, which means it's gonna be what? It's gonna be 0 here. Plus, we're gonna go to what? To potential energy. Our potential energy, we're gonna focus on what? On theta 1. We are going to derivate with respect to theta 1. Okay, so now we have a theta 1 here, so it's m1gl into 1 minus cos of theta 1. So the derivative of m1gl into 1 minus cos theta 1 is gonna be what? It's gonna be mgl sine of theta 1. So we're gonna have mgl sine theta 1. Okay, and then we're gonna go back again. Do we have another theta 1? Yes, we have a theta 1 here. Okay, so we're going to derivate this. So here we're going to have, okay, before we continue, so let me just simplify this part, the L over 2 theta 1. So here we're gonna have 1 over 2 KL squared over 4, like this. KL over 4 into theta 1 minus theta 2 all squared. Okay, so now we can derivate with respect to theta 1 here. So we're going to focus on theta 1. So the derivative of half KL squared over 4 into theta 1 minus theta 2 all squared is going to be what? So we're going to take this 2 and multiply with half. So it's going to be 2 multiplied by half, which is 1. And then we derivate theta 1. So the derivative of theta 1 is going to be what? It's going to be 1. Okay. So therefore we're going to have KL squared over 4 into theta 1 minus theta 2. Multiply by what? Multiply by 1. If I'm not mistaken. Yeah. Am I lying? I think I'm lying, right? I think I'm lying. Let me see something. Okay, I'm not lying. Okay, so when we derivate this with respect to theta 1, it's going to be KL squared over 4 into theta 1 minus theta 2 multiplied by 1. Okay, so here we're going to have plus KL squared over 4 into theta 1 minus theta 2 multiplied by 1, which is going to be equals to 0. Okay, and then now we're going to derivate this with respect to what? With respect to time. With respect to time. Even here I'm lying. It's supposed to be theta dot, not theta dot dot. This one is not theta dot dot, it's theta dot. Not two dots. It's only one. Oh. Here we only have a theta dot, so that when we derivate with respect to time, we can get a theta dot dot 2. Okay, so even here, so here we're gonna derivate theta 1 with respect to time. We're gonna have ml squared theta dot dot 1. Oopsie. Theta dot dot 1 minus 0, and then here we're gonna take this sine of theta as a small oscillation, which means it's gonna be approximate to what? To theta 1. So we're gonna have plus mg L theta 1, and then here we can just multiply this and then get the answer. So KL squared over 4 multiplied by theta 1, we're gonna get plus KL squared over 4 theta 1 minus KL squared over 4 theta 2, okay, or equals to 0. Okay, and then therefore we can group the theta 1 and theta 1 together, and then we're going to have ml squared theta dot dot 1 plus theta 1 into mgl plus KL squared over 4 multiplied by theta 1 minus this KL squared over 4 multiplied by theta 2. Okay, so you can see this equation, we get it when we were using the Newton's second law. We're still going to get the same thing. So when you want the second equation, you're going to say QI equals to theta 2. So QI equals to what? Equals to theta 2. And then we're going to have D. Okay. D over dt into partial derivative of t over d theta 2 dot, okay, minus dt over d theta 2 plus du over d theta 2 or equals to 0. Okay, and then now here you're gonna derivate with respect to what? Derivate with respect to theta 2, and then you're gonna get the answer, the equation. After that, you're gonna substitute whatever that you have to substitute. Guys, you're still gonna get the same answer as Newton's second law when you are using Lagrange method. I think I'm gonna stop here. If you have any question, you can ask me here, or you can just send me a message and then I will answer you. Do you have any question, guys, before we close this session? Just raise your hand. Okay, thank you. All the best with the test. We're gonna stop here, and then I'll share the the link and what I've solved on the WhatsApp group. Thanks. Bye.